Alright, so in a falling film evaporator, air at 40 Celsius and 50 kilopascals flows through a wetted wall column with 100 mils diameter and velocity of 5 meters per second. What is the mass transfer coefficient for the humidification of this stream by evaporation from the wet wall? So we're looking for K, right? So this guy here is asking for K. So the first thing we want is to find K mass for this process. Then the other thing I want to highlight is the 50 kilopascals, because we know this is going to affect our density, right? If the air in this situation is 50% saturated and the saturation particle pressure of water vapor at 40 Celsius is 7,375 pascals, what is the local evaporation flux in the unit of kilograms per meters cubed per second? So the second thing it wants us to find is flux, right? And it's specifying the unit as kilograms meters squared per second. All right, brilliant. Now let's first start with something important. What the hell is a falling film evaporator? So I have a little picture for you guys here, and this is from this website here. This is a private company. I just got it off Google, and this is showing you what that is. All right, and the way this guy works is, let's do this. The way this guy works is you would put your liquid on the top part here. I probably want to get my highlighters here so it's easier for you guys to see. So you put the liquid there on the top, and this can be any liquid. It can be water, but it can be something else. And you have your heat steam coming through here. All right, so you have steam going through there, and you have the liquid coming through the top. Now, you can have the two mixing or touching, you can say, or they can be in separate places. So this can also be seen as just a heat exchanger. It's just a special type of heat exchanger like the ones we've seen before. So what will happen? As this liquid is falling down here, and we're introducing steam that can or cannot be touching it, we know that energy will flow into our liquid, right? So that means that when we get down here by the end of the tube of the pipe, we're going to have some of this liquid in the form of vapor, and some of it will still be in the form of liquid, which will fall down here, right? This vapor, because it's less dense, we know it can travel, and it's going to travel and go into this vapor head here, and here we're also going to have some condensation, so we're also going to have some liquid trapped down the bottom. So these two outputs, they form what we call the concentrate, and this will be, let's say, if we had maybe two types of particles in here, the blue and the red one, now maybe on the bottom one we have more of the blue one and less of the red one, because now it's been concentrated and we separated it with that falling film evaporators process there. Okay, we also have a little outlet for the steam. Where is it? There you go, over here. We have a little outlet for the steam. So this guy that was coming in here to the right, it goes through the whole thing, and then it leaves over here. All right, and then we can repeat that process a couple of times. And our vapor leaves through the top here, and we can grab it over there. Afterwards, we can condense it again, or if you want vapor, you can keep it in the form of vapor. So let me give you a little example of how this can be useful. Imagine we have a little jar with alcohol, ethanol, and oil, like so. These two will mix up. So if we have something like that, we want to separate the two of them, we can just use a difference in density and actually separate using physical separation processes related to the density, right? It can be as easy as that. But if we have a case in which they're mixed up, and mind you that I've had the green to mix the blue and the yellow. Okay, so imagine we have a little mix, and the mix is of both things, of the alcohol and the oil. Maybe a different type of oil, I don't know. But now at this point, what we have to do is either accelerate the process for them to separate like that, that's a possibility, but maybe they don't separate spontaneously. The other option is to actually heat this guy up, and heat up the whole thing so that the first thing that evaporates is the one that has the lower evaporation temperature. But that might demand more energy than we are willing to put in. So this is where this guy kicks in, and that's one of the ideas behind this, because each of these pipes here, each of these tubes that we have here, let me actually draw like one here. Okay. It's designed so that the liquid is only falling on the walls. Okay, so that assists or facilitates or makes it more efficient to absorb that energy coming through the heating steam there, or it can actually assist in the terms of having less mass to be heated up. So instead of having this, you can think of it as we have only a little fraction of this, so only just a little layer, maybe a little layer of this mix on the bottom there. Okay, so a way to separate this, and I didn't make this up, I actually took this from a private company website, the way they do it, right? So to do that, they put this mixture through a falling film evaporator, like so. So imagine the mixture coming through the top here. Okay, that will be our feed, and they shoot upwards. They shoot CO2 because CO2 is not mixing gas and all that. And the idea that this guy is going to heat up, and as it's heating up, what's going to happen is that the alcohol will go into vapor form, and the oil will not. So at the concentrate here, the outlet here, we're going to have oil over here, and the thing that's mixing with CO2 is our alcohol, right? So we're going to have CO2 plus CH6O, C2H6O, right? And then what you can do afterwards, you can feed this mixture. So imagine we have a different container on the right here, and we're feeding in this mixture on another pipe, and the idea of this guy is just to condense the matter, right? So as we feed in CO2 plus alcohol, we know that they have different temperatures of condensation, so we expect our alcohol to condense, and we have liquid alcohol, and CO2 will just remain in the form of gas. So we just separated completely the oil and the alcohol, and you have the CO2 as just a catalyst for this process. Okay, so that's a real private company that does that kind of process, and that's kind of the ideas around this. The idea is that we want to separate mass, right? We have different things, and you want to maybe purify something, or you want to separate something, evaporate something, get vapor out of it. So that's a more efficient way to do it. All right, so back to our problem. What do we need to do? We need to find K and J. So we know that to find this guy here, to find J, that it's going to be straightforward. This is going to be the K that we find in the first part times the concentration, because that's the driving force for this mass change to take place. And to find K, we know that we can relate K to Sherwood's, right? So we know that Sherwood equals K mass times characteristic length, which in this case is going to be the diameter of the pipe, divided by the diffusion coefficient there, right? So it's a matter of finding Sherwood. With Sherwood, we can find K, right? And if you notice, we have an equation for Sherwood. It's been given here, and it's not the best, but I'll rewrite it. So Sherwood is 0.023 times Reynolds to the 0.83 times Schmidt's number to the 0.44. Okay, we're also given the, let's see, what else we have. We also are given the diffusion coefficient, all good. We have the molecular weight of air. So instead of using the, you can relate that. If we get concentration of moles per meter squared seconds, we can convert that back into kilograms, which is going to be useful. And we're also given the, what else are we given? This guy, which looks like M of air, but it's supposed to be the dynamic viscosity, right? That's dynamic viscosity of air, just there. Okay, cool. So that will be mu as opposed to M. So that's mu. So that's why it became an M when it went to text. All right, so we have everything we need. What's our game plan? Game plan is to find Reynolds and Schmidt. Once we have those two, we can find Sherwood. With Sherwood, we can find K, and that's the first part. Then when we have K, we can find the difference in concentration, so we can find J. All right, so let's start. Reynolds number. Reynolds number requires, let me open up my calculations here, requires density, velocity, diameter divided by viscosity. We don't have the density, right, because the density specific mass is dependent on pressure, and we know our pressure change. So I have a couple options here. I can do this, which will give me 50,000 pascals divided by R, and now you can use the normal R you have, or we can do 314, which is the universal R, and our temperature is 40 Celsius, which is 113 Kelvin. Okay, so this guy here is in joules per moles per Kelvin. And we know that pascals can be written as joules per meters cubed. So note that this is going to give me a density in the form of moles per meters cubed. If I want to get rid of that, I can use a molecular weight which was given, and that will be another 0.023. So I'll be multiplying that by kilograms per moles. And note how that's going to turn out well for us, because joules and joules, we forgot the Kelvin from the 313. So kelvins and kelvins, then moles and moles, and we're left with kilograms per meters cubed. And this turns out to be 0.557. 5572 something. I'll just leave it like 557. Okay, so with that we can calculate Reynolds. Reynolds will be 0.557 multiplying 5 meters per second, multiplying, what was 100 mils? 100 mils at 0.1 meters, divided by mu, and mu is given dynamic viscosity as 1.86 times 10 to the minus 5. Reynolds, 14,978. Point something, but let's just leave it like that. All right, next step, Schmidt's number. Schmidt equals, you zoom in a bit. Schmidt equals dynamic viscosity, density, and unit coefficient, all of which we have, right? 0.86 times 10 to the minus 5. Density we just got to be 557, and the coefficient is, where is it? Over here. 1.2 times 10 to the minus 5. Which results in 2.78 something. Leave it like that. With this fellow we can find Sherwood. Where's my equation for Sherwood? Here it is. Okay, and so therefore Sherwood will be Reynolds being 14,978.83, Schmidt being 2.78 to the 0.44. So my Sherwood is 105.4 or so. And we know this has to be equal to the K that I'm looking for, right, times the characteristic length, in this case diameter, divided by viscosity. So if we have all those things, this is trivial, right? Because K mass equals 105.4 times 1.2 times 10 to the minus 5, and I'm dividing everything by diameter, which is 0.1 meters. Or 100 mils, and this will be meters per second, right? So meters per second, and I get, what did I get? 0.012, so 1.2 6565 times 10 to the minus 2 meters per second. Brilliant. Okay, now that we have K, that is answer for part 1, right? So let's put down, highlight down its answer is part A. Answer for part A. And now the part B was asking us what's J. Remember? And if we want to know what J is, all we need to do is find the delta C, right? The concentration gradient, the driving force for this to happen. Okay, so if that's the idea, so let's go jump into part B now. For part B, we're looking for J, and that requires us to multiply K that we just found by the concentration gradient. We were given, the air saturation is 50%, right? And the pressure, the water vapor pressure is 7,375. So if I take a little snapshot, I'm looking at the pipe, we know that the internal surfaces of the pipe are wetted. And we know that if I go in here and do a little snapshot of the air on the middle, about 50% of it will contain water molecules. Right? So over here, where I only have water, don't have, or have the wetter wall, the vapor pressure is 7,375 pascals. And over here, where I have the air, I will have only 50% of that pressure because I only have 50% of the water, right? So 50% of this. Okay, so my delta C is given actually in the form of a pressure gradient. But we know we can translate the pressure gradient into a concentration gradient, right? What is the pressure gradient? Well, on one side I have 7,000 pascals, on the other side I have 50% of that 7,000 pascals. So I can just divide by 2 and I'm going to get a number. And my delta P, my pressure gradient for this case, is 3,687.5. Okay, now what we can do is we can translate this gradient into concentration, right? Because we know that PV equals N or M, depending on the R used, RT, and that at low pressures we can approximate water vapor to be an ideal gas. All right, so what do we want? We want M over V, which equals P. Okay, so the same idea that we did before to find the density. All right, so we're trying to find, let's do this one more time. Let's do it in green, I guess. Delta C will be our delta P, delta pressure, or T. That will be 3,687.5 pascals. And I'll divide this pressure gradient by R. That will be 8.314 joules moles per Kelvin. And I'll divide by the temperature, which we have as well. That's 313. Yeah, 313 Kelvin. And because we want the thing in kilograms, right, because the question asks us for kilograms, we can do the same trick we did before, which is multiply the whole thing by the molecular weight, which in this case is 0.018 kilograms per mole of water. And this can be tricky because remember that we are looking at the diffusion of, remember our diff, or diffusivity, diff. That is diffusivity of water and air, right? And this delta P that we just calculated here, this delta P is delta pressure vapor for water, right? So what we're doing here is we're converting the delta P for water, which we would have in moles of water per meters cubed, into the delta P for kilograms of water. So we know that we have on one water molecule, for every water molecule, we're going to have 18 grams of water molecules per every mole. So multiplying that by 18 grams divided by 1,000 to get kilograms instead of grams, right? And we know that pascals can be converted into the same thing as joules per meters cubed, which allows us to cancel out the joules, the kelvins, and the moles, right? Moles of water and moles of water down here. Okay, so we will get that this delta C equals 2.55 times 10 to the minus 2. And that is kilograms per meters cubed of water. And now we can finish off by calculating the mass flux, which is what we're looking for from the start. J equals K from problem 1 times delta C. In this case, K is 0. And forget 1 point something. 1.26 times 10 to the minus 2. We got before the first part A, and then 2.55 times 10 to the minus 2. And this is meters per second on the K, and we have kilograms per meters cubed on V. Delta C, right? So this is going to turn out to be 2. And answer-wise, 3.23 times 10 to the minus 4. So it's 3.23 times 10 to the minus 4 kilograms per second per meter square. And that will be our answer for the second part here. Okay, again, there will be no problem on us calculating this J without this conversion here, right? We could get a J that would be given in moles per second per meter square, and that would not be a problem. But since the problem specifically asks for kilograms, then we need to do that conversion there. All right, hit me up if you have questions.